So today I'm going to talk about running applications on multiple clusters. I think hopefully many of the audience here actually do run on some Kubernetes clusters, and hopefully you have more than one. So just without further ado, here is the agenda. So first I'm going to give you an overview. The overview is both the problem space and the solutions. And then we'll have mostly two demos, live demos. Yeah, I'm tired of just to play a pre-recorded demos for 2 minutes and do voiceover. Let's do some real thing. And then the two demos, one is for cluster management and one is for application management. And at the end, there's a roadmap and Q&A. So why do you need to have multiple clusters, right? Why not having a huge cluster like OpenAI? They have a cluster of 8,000 nodes that works for them. But actually, not really. They have many clusters of 8,000 nodes. So it's not just one. Even that doesn't work. And there are so many reasons why you need the high availabilities. You don't want to crash one cluster and then everybody dies. Performance, and because 8,000, I don't know any of you have tried more than like 2,000 nodes. It doesn't work well in most cases. So if you want something big, you just have to split it. Scalability isolations, hybrid multi-cloud, I think that's the basic ones. And what are challenges, right? When you have so many clusters, how do you maintain those clusters? How do you? It's a production. And if it's just a POC or like toys is okay, but in production you have to maintain it. There are security patches. That's something that is really always get me. Everything works well, but there's a security patch comes in. You have to patch it within blah 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 days, or your security guy is going to come and yell at you, right? So you have to do that. And then you have this multi-cluster visibilities. Which clusters there? If you have more than, just like you have kids, right? If you have more than 5 kids, you will not be able to know which one goes to school or not. You get this blur. Right? And the team management, most likely when you have multiple clusters, you assign each one to different teams. So who has what? Anyone? If anyone on the online have any questions, feel free to raise your hand. Wei, do you have a question? Okay, thanks. Yeah. So you kind of can lose track of who is on which cluster and the permissions, all these kind of stuff, right? And then on top of that, there's application developers. So that the previous was more like a system admins. The application developers, for the same reason you want to apply your applications onto multiple clusters, just so that one region down will not wipe out your customer or wipe out your customer or the whole service. And the same thing, you have observabilities, networking issues. How do you talk to each other, both east, west, and north, south? That's just all the common problems. So in short, you have to have multiple clusters because you cannot have one cluster solve all. Then that increase your complexity both in application and the system and management. So here is what comes to rescue is Azure Kubernetes Fleet Manager. We recently GA'd that service. It's supposed to solve all your problems, and then you don't have to worry about that anymore. Just kidding. There's no way we can solve that that fast. But we're trying. Right? We're trying. We definitely, that's the first step. We know that this is a huge problem. We tackle it one area at a time. So as I said, mostly it has two areas. One is large scale cluster management, and one is large scale application management. So they're basically two personas, right? One is the Jack is the platform admin. So we have one part is targeting admins who has a lot of cluster. How do you upgrade? How do you make sure they are all in compliance? And the Jill is the application developer who has their applications running on multiple clusters. How do they efficiently run those applications? Either a job which needs a lot of scheduling, or just more stable services, but then you need to upgrade things like that. Okay, without further ado, let's do that part. I think it's already mentioned. Let's do a real demo. So yes, so this is what we call a fleet. The fleet is basically the key concept is we have a, I don't know if you can see that. Yeah. The key concept is we have a hub cluster. Basically, you can think of that as the control plane for the fleet. It's kind of like the a master node for Kubernetes. It's just one level up. We have a control plane, and each member cluster is becoming kind of like a node, quote unquote node. So now this is kind of standard setup for most of the fleet of multi-cluster management system. And then we have some UI, some interesting UIs. So here I pre-created.
Is the subscription like an availability zone?
Subscription.
Are you short subscription member or member doing?
Oh yeah, so it's
Is it like-
subscription.
Is it like a different availability zone?
No, so for this one to join a fleet, we allow multiple clusters from different subscriptions to join the same fleet. So it doesn't have to be confining to same subscription. This is more like an Azure concept. I don't know if you're not familiar with Azure, it's okay. Think of that as a different account, but so different account can join the same fleet. Because what we see that is this and that our specific Azure user, many of them have single account but have many subscriptions. So inside that account, they have many subscriptions. So if you do not allow them to add multiple subscriptions into same fleet, then it kind of defies purpose.
Okay.
But it's kind of details. But anyway, let's show you something real. Okay, so I created this fleet today. Let me see. Yeah, it's called Meetup, right? So that is for the Meetup. Then it's a fleet. This is basically the UI for that. Fleet.
Ryan, would you mind increasing the font size?
Sure.
Thank you.
Is it better? For the online, I don't know if it's we need one more. Okay, great. Thanks, Mike. So you can see that this is in West Central US, and I've joined the 3 members to that fleet. So we have 3. So what I'm trying to do now is do a multi-cluster update. So basically, you can see now they are all at 28.9. So let's do an upgrade because there's a CD coming, or there's a it's going to get out of support pretty soon because Kubernetes you get out of support every like three different versions. So what we have is the concept is called multi-cluster update. So if you can see the graph, basically allow user to, I think that's relatively straightforward, allow user to group different clusters together, and then we'll do stage by stage. It's kind of like a DAG, execution of DAG. Okay, so I will do this one now because upgrading cluster takes some time. And by the end of the talk, hopefully everything is upgraded. Let's see. Right. Okay, just code run. One by one is too simple, just one by one. That's not very interesting. Let's create something a little bit more complicated. So in that, we have a concept called a stage. So in stage, so you can see that I think that this UI to me is very helpful. So it can tell you that each one is called a stage. So let's say just call it stage 1. And inside that, I've already created a group. So you can see that it's a stage, and inside that stage, you have parallel groups. So stage by stage is sequential. But within a stage, you can create parallel groups. So let me create one group. That one I think I've already created. But West US. By the way, this cluster is in East US. I don't know why it's for West US, but this is in East US. But that's not good. I don't want to East US first. Oops. Oh, okay. I go back. Maybe create a new one. Yeah, I want this. I want this. So I want this one. So this one is East Asia. So I'm trying to upgrade. I try to make it more real. So I want to upgrade by region. Right. So I want to go to the East Asia first.
So going by region, is it possible to schedule it by time also?
Yeah.
So for example, like a common use case would be like
Only
go
do it.
business time in Asia, let's do it then at midnight, or start at 1 in the morning and
Yeah.
then cycle.
Yeah, I'm not 100% sure if it is now, but it's definitely we're working on this.
Nice.
So now we have East Asia. And then this one is good. Then create another one. Oh, this one, let me just do the control plane only. The nodes may take longer time. But just do it open only. I need another one, another stage. So I have two stages. First stage has only the East Asia one. The second stage is two, and then yeah, do East one new group. East one. And then I want to create another group. Two. Okay. So I have one. Okay, I need to assign another one. So this is the ES US 0. To create an East US 35.
Yes, you can define all of this in, data form or something, or.
Yeah,
Okay.
yeah. Okay, so I have two stages. Stage two has a parallel one, and say create. Yep. Okay. Okay, so now I have this run. Just want to double check if that run is stage one, stage two. Yeah, upgrade groups as US one. Can you see that from US East one, US 2. Yeah, let's start. Okay, now it's running. Okay, so this is kind of a clumsy way or a newbie way to do this upgrade on using the portal. To me, it's at least give you an idea that what you can do, and we are adding a lot more functionalities like auto upgrades. You can set time. There's a maintenance window on each AKS cluster. Actually, there's a maintenance window which you will say this is how it's duplicatable. I'm having a Black Friday. I'm having blah blah. Don't do anything to that cluster. We'll honor those, and then blah. We have a lot of new features, but this is kind of the very basic type of upgrade. So you can pipeline, and you can see they have pause between clusters, pause between stages, things like that. But anyway, let's leave it here. Give it like 10 minutes, 15 minutes. We come back and see if this succeeds. So this is our one way we are attacking this multi-cluster administrative parts, right? So that we give users some way to automatically upgrade their clusters so that they will all in line. Like the next thing is, as I mentioned, yeah. So this is what I just showed you, and this is kind of the better, prettier version of this flow. You have stages, you have groups. You can say groups are between groups are parallel. Within groups is sequential. Then between stages is sequential. I think it's completely enough to solve most of the problems, we hope. And yeah, instead of this demo, I'm just doing a real one. Okay, now coming back to Jill. She is the application manager, right? So she has multiple she has the application that doesn't want to run on one single cluster. Either it's too big or because she just want to diversify its risk. And we have this same concept, right? So we have this fleet hub cluster. By the way, the previous one doesn't really need any Kubernetes Kubernetes connections. It's purely a management space, right? It's a management core, ARM core. We call ARM because it's a kind of Terraform. It's a Terraform. It's calling the API. The Azure API. But for this one, this is purely a Kubernetes interface. So that is application. You need to talk Kubernetes. So here, basically it's the same concept, but each members now it has an agent that talks to the controller. It's just like think of that as a Kubernetes. Some kind of like we can use some other open source even call it like clusterlet or something like that. That's the same idea, right? And then we have a this is more of our center CRD. We have a basically scheduler. It's think of that as a scheduling mechanism. inside that, we have many ways to, but hopefully very similar or very familiar to any Kubernetes users that we have these affinities, node selectors, prefer before scheduling everything, all the basically see the pod stack and then kind of incorporate there. But the concept is a little, there's some nuances there. I don't have the time to go into details. It will take me maybe 3 hours to go through that. It's just so many nuances. But for now, let's think of that as just kind of like a pod stack. So with that, you can say, this is my application, and I can place it, depends on just like a pod, select your cluster this way, that way, blah, blah, way, right? And in our case, what is a application, right? In our case, application is basically, in most cases, it's a namespace. We place the entire namespace. So we mostly think our model is, in most cases, users put their applications, one single application into one namespace. There might be some cluster role binding, cluster role, the webhook configurations may need to be associated, but it's okay. But the central one is that namespace contains, in 90% of the case, you have a deployment, you have a service, you have some secret configurations, role bindings. That covers a lot of most cases, yeah.
So Microsoft provides the compute for OpenAI, some part of compute, I think. Does it also use similar cluster configuration using Kubernetes?
It uses AKS. OpenAI just use AKS. AKS is the Azure Kubernetes,
Okay.
just normal Kubernetes
Oh.
service, yeah. So it's the same. And we're also talking to them about using this mechanism to place. Currently, they're basically eyeballing clusters, say, okay, I feel like this cluster today is pretty free. Let me run some training jobs there. But we are saying that this might not be the best case. Yeah. So this is trying to help other teams that say, I have many clusters. Today, I don't have GPUs here. Tomorrow, I want to save some money for various reasons. If they want to find some cluster to run, this is a way to help them. Any other questions online or?
Sorry, so this is the namespace in one of the clusters, or you can also replicate in? It can.
The scheduling is the magic, right? You can do tons of different stuffs. I will demonstrate that with a very tiny bit of their abilities, but you can do all the stuff.
Okay.
And definitely more than one if you want more than one. And here is kind of the, and then we also have a network, but I think we don't have time for that. This is the backup demo. If my live demo failed, let's just watch this one. Okay, let's see if I can. Okay, I still have these. Okay. Let me see if I can. So this one is
You increase the font size, please.
this side.
Sorry.
Let's see. Yeah, see, I have. Wow, then a big. Now then. Let's see if I can. Oh, I can still go back. Okay. Yeah, let me just first check. Okay, so at least this one. So this window is for the hub cluster. This is connected to the hub cluster. This kubectl is connected to the hub cluster. Then we have, if you look back to this, this is the same. This is the same fleet that is. But I'm just check if it's filled. Okay, we could check back. So this is the same fleet that has, if you can see, it has 3 clusters, 3 member clusters, 2 in East US, 1 in East Asia. Right? So this is in East Asia, this is in East US, this is in East US. Then, do you have anything? Okay. So I pre-created a deployment there. Okay. So a pre-created deployment there in this namespace. This namespace is called Meetup. Right. This deployment doesn't have any part, doesn't have anything because we killed all the. We basically modified the controller manager to not do anything on the deployment. So that's the hub cluster. Think of that as a database or just a way. Think of that as a place for you to park those YAML files. It's not going to do anything for you. And then the key concept is called CRP. So this one, let me apply that one, and then you can see it from the
I think we should zoom in.
Zoom in.
Zoom in.
Font size.
Bigger. Then I lost this good. So here we have this. Yeah. So this is the one that I just applied, and you can see a YAML. Okay. Okay. So what this says is, this is the kind of the interesting part, affinity, right? So this, what it says is, this is a class affinity. What this is, we prefer a cluster with, descending means we prefer a cluster with higher node count. Right, this is a property called node count, so that's with descending, so we prefer the node count. And then required is if matches label with East US. So basically, we want to find a cluster that is in East US and has more nodes. And here also says this, we will just pick one. And this says the resource selectors is namespace meetup. So we say that on a hub cluster, there is a namespace called meetup. Place it to a cluster in East US, and we prefer a cluster in East US that has more nodes than others. Did any questions on this?
More available resources on nodes or just more nodes?
No, node count. So it's node count. We have different properties like I can. Yeah, good question. Let me show this. Let me see if I still have that comment. That comment is a little bit tricky to type, so hopefully I still have it. Yeah. Okay. So these are the those are clusters customized CRDs basically. And you can see the node count on East US, one has 3 and one has 1. And we also have cost based, like per CPU cost. We did some pooling from the Azure website, calculate some cost, and also have available CPUs. So actually, because I already applied the CRP, I think it should already be on, which one has the more account? 3. So it should already be on 3, on this guy. So it's 0, so this is E0.
And it's extensible as well. So it need not be just on standard metrics. So the way in which we're thinking about it is kind of similar to Kubernetes strategy itself, right? So we can plug these like external metrics as well in the future if needed, and then have the fleet orchestration basically rank out of those clusters and then schedule.
Thank you.
Aware of the node pool configuration in the sense that, well, like capacity, right? Like you would probably have some kind of autoscaler set up on your node pool. So
Okay.
That will change.
because I mean, it's nice to know what nodes are already up, but that's not the whole story, right? Because you could have a whole pool that could max out to 1,000 nodes, whatever it happens to be, right?
So what signals are you looking for in terms of the node pool scaling and the readiness?
I was just wondering
It's like both,
if it's aware of those
Yeah.
things. I would imagine that it is, but yeah.
So if I understand correctly, you are talking about this quote. Currently, I only have 3, but I have the abilities. I have a Carpenter or Nova there, right?
Well,
Because-
or even just how you set the scaling limits on your node pool period too, right? Like
Yeah.
use, you could have like, we can have, 10,000 of them, but for this node pool, I wanted to only max out to 100 because I want to be able to spend that much of it actually.
Yeah, as Zhang mentioned, it's we support any kind of customized metrics. For example, this the CPU count is customized one. You have agents, as I mentioned, in the hub member cluster, you have agents. That agent can define, say, I want to expose certain metrics. And then the hub side, we can collect it, and then you can select it. So as whatever you expose can be used here to select. So it's kind of flexible, but your case definitely is something that we know that.
And that plugs into your specific account's rate card too.
Account what?
So like the Azure, the ARM presents a rate card API endpoint, which lets you hit it with your credentials to find out what your price is, which might be different than what's published.
Yeah,
right?
yeah.
Like if you have a Mac with Azure, for example,
Yeah,
you
yeah.
might get 7%, whatever
Yeah.
discount on.
So currently, we don't support that. We're using as I said, the public ones. But for private one, I know, the detail is, it's actually a lot trickier than just me having 7%.
Yeah, because yeah.
So a lot of details. That's why we didn't go there in the first round. But we are definitely plan to do that if their user coming.
Yeah, and to that point, right, when we were discussing about the cost-based explain. So the thing is, these are all different inputs. So public API based one, it was a bit more straightforward for us and like those additional variables are there. So we play with it. But I think, yeah, it's a requirement that like we take into account the different technicals for specific customers there. We did kind of a spike on that. It's a different set of APIs, so we need to work on it, but it's doable.
Yeah, I mean, that's what KubeCost does. Like if you install KubeCost on AKS, you have to jump through a couple of extra hoops in order to get it to connect up to your rate card API, but it can do that too.
We even like had KubeCost in that document as well, that we were considering the options. It's just
Yeah.
that we're like, okay, we need to get that, we know we can get that. It's just a matter of time.
So now let's change this affinity, right? It was preferring the descending. So let's try preferring ascending. This means we want to pack that into a cluster so that it can be more efficient. You should see this should move to this guy in. Let's see how fast this goes. Screen not moving. So take a look at this. Oh, Apple, I think it's another type. Temple here. That's why we need to chat GPT. Copilot.
That's stay on brain.
Okay. Yeah.
I was recording the session for like something today to submit and Copilot is narrating. So just I have to record only the difference. So like it does not. And I heard it once and I'm like, okay, this voice is way better than mine. I'm never going to be speaking like it like this.
That's crazy.
It's moved to the other side, right? So this is live demo cloud is still likes me. We have a lot more stuff we can show, but I think we are kind of out of time.
Did your upgrade finish?
Yeah, upgrade failed.
Oh, upgrade failed.
Yeah, I thought that.
So
Hey,
that's
that's our life.
essentially your question I was gonna have. What is it? Can you define like what it should do if one of the steps in the pipeline fails? Like, can you say,
Let's take a look what the
Proceed.
procedure is failed.
You mean to say in terms of the upgrade run?
well, so he created like a multi-step pipeline of doing the upgrade. So I was just wondering, like, if step one fails, does it,
Should it roll
Yeah.
back or?
does it try to roll back? Like, can you define that as part of the policy of it, or?
Yeah, so right now we don't have extensible hooks into that whole workflow. That's something we can extend. In terms of rollback, not just at the fleet level, but at the single cluster level as well. Rollback is a semantic we don't make intentionally like support that. And it goes back to Kubernetes itself saying, hey, we don't recommend downgrading a rollback, right? Because the thing is like the moment you, let's say it's a Kubernetes version like upgrade, or even for that matter, node would like upgrade. If it's like in place and like especially Kubernetes minor, it's like you're doing it with the same cluster, right? The moment you go to a new minor version, there are new set of APIs that are like previous APIs from the older version that get duplicated. So returning back, rollback basically gives the impression that you'll be able to like return back to that like working state.
It's not like.
It's a myth,
Yeah.
right? It just does not happen.
But what about something like stage 1 succeeds, stage 2 fails? Are you gonna force me to go back and redo everything, or can it be like GitHub Actions where I click a button that says rerun failed jobs, because there's always failed jobs in GitHub Actions pipelines? Like, is that like an option for it?
That's something we're getting towards.
Okay.
So like the next month, we are going to introduce skip semantics, like
Nice.
you to get the skip the clusters and like the reinitiate upgrades. And like even if you start the restart the entire update, I mean, there were already a previous set of clusters that went green. It'll be a no op for them. So those
Yeah.
will skip. So those are already set up.
Okay, thanks.
And I was used to be in the Azure pipeline stream and like which became GitHub Action. So a lot of these like are kind of similar.
Yeah.
The one additional benefit that like gets involved like with this whole thing is the node images keeping them all consistent. And in future, like if we want to extend these things onto, let's say, blue green at the node level or blue green at the cluster level, we can expand those out like with the awareness of share.
Yeah, so this is a good segue that here's the feature roadmaps, a lot of good suggestions, a lot of practical, I guess you have a lot of clusters. And have the pain. So we know that we understand all these pain points, and they're a lot more than what we offering now, but we are actively working on a lot of solving those problems. So we, in addition to the features that Zhang mentioned, we also have a more intelligent application placement. There are just tons of them there. And we can allow you to browse multiple resources. I haven't demoed that yet in the portal. That now if you place it to one, because currently you see I'm using those primitive shell scripts or the command lines. But then on portal, we actually allow you kind of like, I don't know if any of you have used Argo CD, Argo things, and you can see these coming to different clusters. You can click on that. So I think it gives you a little bit better experience looking at different applications. We will add Arc enabled Kubernetes clusters, but if you don't know what Arc is, it's fine. And then also the very important one is the network. So we have north-south network coming at certain point that for multi-clusters, and you can actually direct traffic between applications. Because currently, if you just move applications, the traffic doesn't go with it. It kind of not really useful. And that works for jobs, but not really work for like services. And then we have multi-cluster service mesh and identities. Now, identity is something that you do not want, when you place the application into multiple clusters, you do not want to assign everybody a different identity. And then when it talks to backend services, they come as different identities. And you kind of don't know, sometimes you need it, but sometimes you don't want, you just want them to talk to the backend and same. And all the multi-class auto upgrades there. Finally, there's some links. If any of you are interested, you can play with it, read the documents. We have both of these. The data plane solutions are open sourced. If you have any problems, you can raise issues, give it a try, and works on any clusters, Kubernetes cluster, not just Azure. Finally, yeah, any questions?
Just 2 slides before, I have one question for the room. So among all of these, like which ones would be like higher in priority? And I just add one additional point to the identity one. So we're also like currently working on like Microsoft hosted like managed CA and handing out like SWIFTs so that in like where X509 certificates are supported, like and for the service mesh as well, we can use that where we map the cluster name for an entire like set of clusters, and then we have the same identity like handed out to the same workload and the same namespace across all those clusters. I'm just curious, like given the totality of the roadmap that we have, and like just wanted to know, like because most of you are like already working on like Kubernetes-based platforms, what kind of problems are like similar or common for you folks as well, and where is most of your time spent, and like what's more important?
Can send out a survey like.
Yeah.
It'd be great. Yeah. By the way, I don't know if you introduce yourself. This is.
No, I joined a little bit. I was trying to figure out parking.
But this is Shashank. He is the PM for the Azure Leads.
Nice. Right?
So you can hear the product mind there.
Yeah. Yeah, we have some
talk later maybe today, but we have some solutions to some of these. So we're not running on Azure, but we had to solve some of these problems in other
Yeah,
platforms. So happy to talk about these too. What did we end up doing? But I think seeing some native support to some of especially the identity and the upgrades and replacement from the platform would be something interesting for us.
thank you very much.
Awesome. Thanks, Ryan. The next speakers are Anne and Dave, talking about scheduling, RAG, checking out.
So Ann and I are here to talk about resource-aware policy-based scheduling for GenAI and RAG applications, specifically in production. So there's been a lot of talk throughout the space around GenAI applications and RAG applications, and a lot of people are actively developing them. They're running them, in-house. But what do you do, or what should you do when it comes time to actually go into production? Because there are some different things to consider versus when you're just running it internally. So we, a few months ago, talked about this idea and thought it would be a great idea to come up with kind of a reference architecture about how you might go about doing that. And that's the focus of the talk, is to explain the reference architecture for deploying these kinds of applications in production. We'll start with a bit of an overview on GenAI and RAG just in general for folks who may or may not be aware, right? GenAI obviously is short for generative AI. Large language models, I think probably most people are familiar with by now. The focus of the talk is not necessarily an ML talk, but if you have questions around large language models and some other AI specific things, and probably can talk a bit about now. A little bit more retrieval augmented generation. That's also very topical these days. So you kind of think of it like if ChatGPT has a working knowledge of how things are from a certain point in time, like its timestamp in time. With RAG, you can layer on additional pieces of data, specific pieces of data on a foundational model, and use that to improve the kinds of results that are returned. So, what's good about RAG? It reduces LLM hallucination. I don't know if anybody's ever tried to make ChatGPT hallucinate. Am I the only one?
No.
It's fun if you can achieve it. It's actually, there's some ways to do it. It's kind of fun. Also, too, be nice to ChatGPT. If you curse at it, it tends to change as well. Don't ask me how I know. I have friends who tell me. If you use RAG, you can also avoid LLM retraining and fine-tuning costs. So think about the kinds of costs that are involved in rebuilding your large language models. Right? These are all very compute-intensive types of operations. So instead of rebuilding everything from the ground up, how about you just layer some stuff on top of it instead? All right. How much time do we have?
30 minutes.
Okay. All right. So I should stop. I should get more focused. That's what I should do. Okay. So there's a couple different options for hosting a production LLM and RAG application. There's public APIs for hosting it that you're probably familiar with, OpenAI, Cohere, Gemini. But another option would be to self-host it. I'm a big fan of dog food and dog fooding in general, so this kind of speaks to me more so than anything else. Some of the advantages of self-hosting: cost, scaling, performance, control, privacy, all the kinds of usual benefits that you get when you choose to do things yourself. There's the huge caveat whenever you try to do things yourself too, right? More complexity. So caveat emptor, right? Buyer beware, self-hosting, more complexity. There's no free lunches in anything. And this is true here too. So you have to find a way to handle this complexity, and that's kind of what the reference architecture is really all about here. Is our recommendations on how you might go about handling that complexity when deploying your app across multiple clouds and multiple clusters in multiple clouds. So here's kind of a high-level block diagram of some of the major components of a GenAI application, a RAG application. So you have a raw data source. This could be any kind of unstructured data. that you want to turn into vectors. That would happen in here for the vector DB ingester, and then eventually would get into your vector database. Your vector database would serve as a source of data for your LLM and RAG serving component, which is what your front end would interface with. And then you have an LLM that's running separately. Each one of these components has different kind of compute and CPU requirements, and we'll get into those a little bit later on. That incidentally is a big part of the complexity that you have to contend with when you try to run this yourself. So the first two components up there at the top primarily run on CPU resources, and they're only used periodically. I'm not aware of any obvious use cases where you would be constantly adding additional data, turning them into vectors to augment to do RAG, basically, to augment your LLM. It seems to be most of the use cases that I can think of, and I've heard people using is that it's kind of more batch oriented. That may change over time, but currently we expect that to be pretty infrequent. The rest of the middle of the stack can run on pretty generic CPU resources. When you get down to your serving your LLM model, you're going to want to take advantage of the acceleration from GPUs and high availability concerns too. So you can kind of start to get the picture about how complex this is going to get. So multi-cluster Kubernetes is a great way to meet this demand, especially when it comes to trying to achieve higher availability, also trying to optimize your costs. Costs to run the same kinds of compute across the three major hyperscalers varies pretty significantly, and it varies pretty regularly too. I'm not sure how aware people are about how often the prices change, or even just compute. And Kubernetes, yeah.
Hi, one naive question on this. What is the significance of multiple clusters here, and why can't I put all of the resources that I want in a single cluster itself?
You absolutely could, but then you have a single point of failure, and when you're running in production, you try to avoid that. You could do a single cluster that's maybe availability zone aware, so you've got some protection, right, with availability zones. I'll just give you like a real world example though. When I'm running Kubernetes clusters in AKS, typically AKS failures are not availability zone failures. It's the whole region that goes out. So I've got one cluster that's spread across multiple availability zones, and I feel like I'm doing pretty good, but then the whole region goes down and I'm down. Which, depending on your use case or your needs, like maybe that's a risk that's okay to take. But if you have really high uptime requirements, you would want to take that risk. So not only would you not just deploy only to AKS, like you would deploy to AKS, you deploy to AWS, you deploy to GKE, so that you could have one in each cloud provider. And then you would take advantage of multiple regions in each one of those cloud providers as well.
So is there like a huge redundancy happening here across multiple regions? So compute remains unused.
Yep. Scale it down when you don't need it. Scale it up when you do. And the Kubernetes cluster autoscaler that we're going to talk about later on can help you do that. You can define the policy for how you want it to do that. And it's very easy to spin it up and spin it down.
Okay.
So the workloads that you're running on these multiple clusters, are they all isolated in nature, or do they also need to talk to each other? The workloads across the different things. I
mean, it depends, I suppose, on what you want out of it. You could just basically create a mirror. So I think that is an option that Nova can do. You can create a clone of your environment in another cube, for example, if you wanted to, in another cloud provider. Or you could spread the load around and have, for example, you could have your vector database ingester in one area that could be talking to a vector database in another area. And you could, however you want the topology. We don't really get into exactly where you should schedule these things across multiple clusters and multiple cloud providers, only that you can. Yeah. So you define the policy if it's in your application's best interest to do that. Like maybe it's more cost effective, a great example, maybe you want to take advantage, maybe you want to run on ARM because every cloud provider these days is offering ARM CPUs for way cheaper than Intel and AMD. But only one of them has, for example, like streaming accelerations or something like that, because not everybody's using the latest version of your ARM CPU, right? So then you deploy, okay, I only want to deploy my workload that can take advantage of those accelerations to that one cloud provider, and then something percent for other ones.
Okay.
Those kinds, like, that's just like one example, but that kind of stuff happens pretty often. Like there's some variation in what's available and what's most cost effective in each one. So with a multi-cloud aware cluster autoscaler, sorry, it's a mouthful, like you can find the policies for all these kinds of things because it's aware of the prices of these things too. Okay. Which kind of ties into what you guys were talking about earlier. There's some definite overlap. Yeah.
One more question. What is the difference between question and prompt in this context? Please, the last one. So user asks the question to LLM+RAG serving. LLM collects the context, previous context. But what differentiates question and a prompt?
So the prompt packages up the question and the context that were fetched.
Oh,
And so the prompt would be like, hey, Mr. ChatGPT, please give me the answer to this question and please use this context
okay.
and please don't use any other information. So the prompt packages those two together with some things to try to control the LLM model.
Right. So it's like a string concatenation that you would put so as to retrieve the exact result and to avoid hallucination.
That's right.
Cool.
Okay, I think we talked about that one. Okay, so we also kind of started talking about this here, right? So the way that we're suggesting to approach how to manage this across multiple clouds, across multiple Kubernetes clusters would be a resource-aware policy schedule, policy-based cluster scheduler. And this is going to help you efficiently manage all of this complexity because that's what this all comes back to. It all comes back to when you're trying to roll this all yourself, you've got a lot of complexity. How can you manage it? And most important, primarily this talk is going to focus in on Nova. There are other different tools that you can use for this, but we're primarily going to focus in on Nova. There's some other ones you can take a look at, Karmada, KCP, etc. Okay, so some of the components of Nova, there's a control plane piece that's installed in one of your Kubernetes clusters. And then there's various agents that are installed in your clusters that you want to scale up and scale down across different places, kind of similar architecture. And we saw earlier, or at least hints of potentially with the Fleet Manager. Seems like that's probably implemented in a similar way. And it's resource aware and policy based. So it knows about the resources that are available in each one of the cubes, and you can define the policy that you want to determine its behavior in terms of where it's going to schedule different workloads across all the different clusters that you have available. And it works for all three of the major cloud providers. Is anybody else?
Yeah, so Nova itself works on any Kubernetes cluster.
Okay.
But if you want to use just-in-time clusters where you want us to create new clusters if you need them, then it works for these three cloud because those are the ones we know how to create new clusters on. This is an option.
Yeah.
Do you use like cluster API? Is that like?
We don't actually.
You don't, okay.
But we call the interfaces that create clusters directly for those clouds. Yeah.
Is Nova backed by Terraform because it's supporting multiple workloads?
I don't think so.
No, we're not using Terraform.
Oh, so you wrote your own construct?
We wrote our own.
Okay.
Yeah.
It's probably a really good decision too these days.
Yeah.
No, nothing wrong with IBM, but a lot of things go there to die. Okay.
Could you go one step before?
Here?
Yeah. So your control plane, can that actually be run on any of the cloud providers? The control plane, and can it be
Even your own cube too.
Yeah, it's just completely a Kubernetes thing.
sure? And in terms of like redundancy for your control plane, so could that could you run your control plane on like multiple cloud providers?
Yeah.
I'll let Marjorie take that.
Yeah, so, for multi-AZ redundancy, it is feasible for multi-cloud or across region. We recommend, currently the best practice recommendation is use something like, I forget the name of the project from Dentsu. There's an open source project for basically the state management we offload. We don't take care of it. So,
Yeah, that was going to be my next question.
yeah.
Okay.
We haven't gotten to customer use case yet where we need it across the region, but we have this poor man's version of we can outsource to state management something external, then let me get the name of the project. What?
So is this control plane like a driver in Spark and agent is like an executor in Spark? So control plane gets the work, it distributes the work across different agents.
It's just a database server.
Okay.
That's exactly what it's like. I
Sorry.
certainly, I mean,
CRUD calls.
local resources.
Okay.
Yeah, it's just gonna have like source of truth of all the CRUD calls.
Got
That's what.
Yeah.
So what takes care of the reconciliation between agents that are running in your data plane, essentially all the workload hosts and the control plane?
So the control plane, basically, when it wants to schedule on a particular workload cluster, it puts that work in a place in the etcd of the control plane. And the workload clusters have agents that talk, they know how to talk to the control plane, so they know how to pick up the work.
This is.
And then they write their status,
Regular Kubernetes.
regular Kubernetes, and then they write their status back to the control plane.
No,
etcd.
the question that I had was, depending on the cloud that you're like talking to, your control plane could be on one cloud and your data plane, your workload host could be on the other. Then you're talking across like cloud providers, right? Like you egress from like one cloud and then ingress into the service gateway of another cloud. So what manages all the, IP routes and there is a non-trivial amount of like network management that needs to happen.
Right, I guess this is basically, you need if you're using multiple clouds, which we're not using in this particular talk, but if you're using multiple clouds, your agents need to know how to talk to the API
Exactly.
server of this control plane, not the EKS control plane, but our Kubernetes that's running, our control plane is running in a cluster. So as long as you can talk to that cluster, our cluster, you're okay. And I may be missing your question, but you're not talking to EKS's control plane. You're talking to Nova's control plane, which is just an application.
No, my question was a little bit more simpler. Like, are all the like routes managed for you, or do I need to be like aware as an operator of Nova? Do I need to be aware to kind of like write these cross cloud like policies? Because the policy language itself is like going to be different for making this type of cross.
Yeah, so Nova doesn't manage the network routes for you. Nova enables you to schedule something like Cilium cluster mesh or Istio multi-cluster service mesh. So Nova can deploy these components for you. You can say, here is Cilium multi-cluster service mesh. Hey, Nova, deploy it on all my blue clusters that are running on AWS, 1/3 of which are running on AWS, GCP, Azure. And the networking solutions will set up your east-west routing for you, but Nova itself is not setting that up. So Nova's primary vision is for side view of all your workload fleets and managing compute. Just because it has God's eye view, it can deploy multi-cluster networking solutions. It can deploy multi-cluster storage solutions, but we offload the onus of networking and storage to solution providers in those domains.
Okay.
Does it answer?
Yeah, that does.
Fine. One more question, if that's okay.
Yeah. Interactive talks are the best talks.
So you mentioned every agent writes back the state to the control plane etcd. What state is that? Is that like these are the pods I'm running? This is their state, or it's just its own state, like healthy or not?
It writes back So it's kind of two things. So when you placed something with Nova, Nova decided, oh, I'm going to place this on workload cluster 1. So, it basically sets up for workload cluster 1's agent to see that it's got this new work to do. So workload cluster 1 pulls that thing, let's say it's a deployment, and workload cluster 1 deploys the associated pods with that. So workload cluster 1 writes down back the status of the deployment. Like the deployment was successful, there's 2 replicas running, which is the number you expected, and so on. Now, optionally, it can write back the status of all the pods it cranked up. It didn't schedule those pods, it scheduled a deployment. Those pods were scheduled by the individual workload cluster, so it puts more load on the control plane to write that back. So we don't write that back by default. We have this thing called backprop, which is an option that will write back those additional details. But in many cases, you don't need those details. You just want the status of the things in place for you. Yeah, Brian.
Follow-up question on that. When you say write it back to who, where?
So basically, there's an etcd associated with the Nova control.
Yeah, but then what object type is it?
Oh, we have custom resource objects that are kind of getting things and then putting them back into the original object that was placed.
So user needs to write, so they want to pick a place that's deployment to some places, but they don't write a deployment, they write a custom resource.
No, they don't write it. They write it. They have a policy, like deployments of this type should go to this kind of cluster. So they write a policy. That policy is given to Nova control plane. And then they write a regular deployment, but attributes of that deployment are picked up by the policy batcher and sent to the workload.
So it's written back to that policy.
Yeah.
It's written back to the object they placed. They placed a deployment. They see the if they did a kubectl get all, they would see their deployment with the status as if it was running on the control plane. It looks like it's running on the control plane, but it's running on the workload.
That's my question.
Yes.
But then if you place that into 2 clusters, how do you come back?
So that's the interesting thing. Let's say you wanted to spread schedule. So you wanted that deployment to run on 2 clusters or n clusters. And then you get back a really funky thing.
Yeah.
Like let's say there's 2 replicas in there. So let's say there's 3 clusters and we spread schedule. It'll say 6 are running out of 2.
Yeah, exactly. That's my question.
But we actually like it, but I'm not sure, whether you as customers would like it, but the idea is we're showing you got, n replicas and you got them across 3 clusters. You got the replicas you asked for the deployment and you got them across 3 clusters. That's what we're doing right now. I'm willing to take feedback on this, but it seems customers seem to like it. Okay.
All right, so we talked about the high level block diagram of our RAG application. This is just talking about some of the different open source software components that you could fill in for each one of these layers and pieces of your RAG application. Again, keeping with the theme that the whole point of this presentation was to think about it as a reference architecture implementation. So try as much as possible to avoid picking any winners or losers in terms of specific vendors or components or anything like that. So the demo that you all can go to and grab it from GitHub if you want to. You can grab the containers, the Docker files, all that kind of stuff and play around with it if you like. And there's links to all of this in the talk. Is based on the open source software offerings of these things. Yeah, I think we can, maybe in the interest of time, we'll move. So talking about how these things are packaged with Docker, taking into some of the considerations that are required for each one of them. So again, like our LLM serving component is going to need to be GPU aware, and a few other pieces. Okay, so talking about high availability, back to kind of earlier your question about why not just use one big cube. So thinking about high availability, this is kind of would be our proposal for a pretty highly available deployment for this RAG application, taking into consideration some of the availabilities for each one of the pieces of the puzzle, right? So one cluster for your vector DB ingester and your raw data source, again, because we anticipate that being a fairly infrequent kind of thing that operates. If it happens to be down, wait for the next batch to run to come through, and that's fine. Your user-facing component, your API, LLM, RAG serving component, those you want as high availability as possible, obviously. So 3 clusters for that, maybe spread them out across different regions. Even in this case, we're talking about locating them across US, Europe, and Asia. And then down at the bottom, our LLM serving component is another critical piece of the front forward-facing infrastructure, but it's also very expensive. So maybe we don't triple replicate that. Maybe we just double replicate that instead. Yes, sir.
Then how do you route? What's the route between these 3 clusters and 2 clusters? If I understand correctly, basically user goes to that 3 clusters. One of them and then forward that to the.
User would go to like a load balancer sitting in front of those 3 clusters, and then
Then it will forward to the real serving when and come back and return to you. So between these 2 and the 3 and 2, how do you route these?
So when we, in the setup we have, the 3 clusters are used to put the 3 copies of the front end in the 3 regions. And they're talking to one of those 2 clusters. We didn't duplicate the GPU component. We just had one copy of LLM running. And when we deployed, we told the 3 front end clusters the IP address of the LLM they should talk to.
Oh,
And that's a service point in front, a load balancer in front of one deployment of the LLM.
So it's active and
active passive.
active passive.
Yep.
I mean, you could with various different kind of load balancer implementations do active or however you want to do it. Okay. Real quickly, we'll kind of talk about in very simplified terms, the kind of phases of deploying actually, all the different pieces. This is maybe a little bit hard to see, but there's numbers in front of each one of these steps for the different components, and those kind of represent the order that we go in. So number 1 would be placing the model and creating the basic kind of plumbing that you would do whenever you deploy anything across the Kubernetes cluster, set up your namespace, then place the model there, deploy your pods. The next thing you would do is go down to your LLM serving clusters and deploy that behind the load balancer that we were talking about a moment ago. The third thing would be to go over to your vector database ingester. So that's down over here, get that set up. And then last but not least, place all the remaining workloads and load balancers in front of each one of them. So again, like this would all be the kind of thing that you would define in policy.
Wouldn't this ingester be better off as a lambda that's like spinned up when needed, dies when not needed?
Sorry, can you repeat that part?
This ingester, it could be a lambda that's event triggered, right?
Yeah, absolutely. I mean, if you can find another way to do something like that, like a batch job, there's a lot of different ways that cater to batch type operations and batch type work. You know, serverless functions is great, right? You could even deploy a Kubernetes cluster that has, what is it?
Scale to 0, I think.
Yeah.
This is a scale, in this example, it's a scale to 0.
Yeah.
Scale to 0 is AWS lambda equivalent in Kubernetes. Scale.
It means no nodes. It means the cluster exists, but there's no nodes, and you pay by most providers you pay by how many nodes you have.
Right.
There isn't like a base fee just to have the cluster defined period, although
There's 10 cents an hour.
Yeah.
10 cents an hour to have a cluster with no nodes.
Sorry,
In
this
that
question
case,
is naive. I'm new to Kubernetes, but I know AWS, so I'm trying.
Yeah. Yep. But that scale to 0, I think is supported across. It's not just a. That's not
Yeah,
just
all of them are 10 cents an hour to scale to 0.
Yeah. I guess that's kind of
Yeah.
I'll remember to mention that next time. This is a single step to remove it all. One step undeploys it.
Since it was all in the same namespace, kind of like what Ryan was talking about.
Yeah. Oh, that was another important point.
Yeah.
One namespace. The idea behind that is for a lot of these kinds of applications and workloads, you would want to run multiple different versions of it at the same time to make improvements. If you're familiar with kind of running any kind of AI, ML type workloads, you want to deploy multiple models, tweak the model, deploy it with the same data, get some more usage on it, tweak the model, run it again. That's kind of the idea behind this is you'd have push one namespace with some hash. That's this version again. Makes it easy to keep track of. Yeah, okay, so I think this is the last part before the demo. We talked earlier about focusing in on open source software solutions for all the different major components. When you're running something in production, your executive team may not be super comfortable with running everything on open source software. They like the warm and fuzzies of having a support contract. So there are commercial vendors, in this space who will happily sell you various different kinds of services and support contracts to go along with them. We've listed a few here. Some of them you may know and may have used, maybe some of them you haven't. But it's always worth knowing, again, thinking back to, we're going to production now. When you're going to production, you may want to select a commercial vendor for some of these components instead of using open source software for all of it. I think maybe Anne can talk to you about some of the pains that she went through in building some of the demo with one pieces of open source software that we did. And I think that's it. Okay, more or less, right? And we're trying to keep, we're already a little bit over time. All right. So we have a bit of a demo.
Yeah, and when we say demo, it's not a demo like,
Not like,
we don't have the nerves of steel that Ryan has. So it's not a live demo. And it's not even a recorded demo. It's basically pieces, parts that are available in a GitHub, and we'll show you how to use them yourself. But we don't have those that background. So anyway, for the choice space that Dave just showed you for the reference thing we're going to show you, we chose in this example to use AstroDB, but we also in the GitHub repo, and these links all go to the GitHub repo, we also show you how to use Space along with, pickling and unpickling DS3. And in our example, we just populate the database at one time at the beginning of the deployment of the model. We don't update it later just for the purposes of demonstrating this. We used a single cloud for this particular example, which is EKS. Sorry, guys. But anyway, we can run it on EKS, but it's on EKS. And for cluster suspend resume, which is an option for the Nova control plane that can put workload clusters in suspend resume. You can turn that completely off. It's off by default. You can turn it on, but keep the control plane of the cluster up. So that's the scale to 0 at the 10 cents an hour. Or you can have Nova completely remove the cluster and recreate it when you need it. Obviously, there's a lot of latency there, but you don't even pay the 10 cents an hour if you want that option. So we went with the middle option, which is we turned on the suspend resume on the cluster, but left the control plane of the cloud vendor up. And we triggered the operations manually. We're not doing GitOps here, but you could hook this up with the GitOps. Disclaimer: this is not about my mad ML skills. It's possible that your LLM model that you might choose might be different than the one I chose. I chose an open source model that worked fairly well. A different resource sizing might be tunable you could do. So you'll see that. So here's example 1. Let's say you want to roll out version 1 of your model. Then you want to roll out version 2 of your model and see if it's better. So you let it, bake, you watch it. Maybe some of your traffic goes to one, some of it goes to the other. And when you're happy, you retire version 1 of the model because version 2 can take over all the traffic. So that's the scenario. So this is intended to demonstrate, that doing this with multiple clusters can be seamless with something like Nova doing the controls for you, and it can be operationally simple, but you can have that isolation of the different resources that are there for different purposes. So at the beginning of the world, we have these 6 clusters on EKS. We have the first 3 clusters are for the front ends to talk to users in different regions of the world. The next 2 clusters are GPU clusters that in 2 regions that happen to have a fairly good amount of GPU of the type that we need. And the final cluster is the ingestion cluster. This is only used when you're deploying a new model and you need new database ingestion. Otherwise, that cluster's in standby. So you see at the beginning of time, all the clusters are ready, meaning they're all online and ready with all their static resources available. They're all idle because at the beginning of the world, they're all don't have any work to do, but they're not in standby because they haven't been idle long enough to put them in standby. So this is the beginning of the world. Just for fun, we let all the clusters go into standby. Just so that we could start the demonstration with them all in standby, have them brought up and have the clusters run there. So what happens when you deploy a model? Well, it's a one-liner. Basically, we have scripts. These scripts are in that GitHub repo. But basically, you say, what's the model namespace that I want to deploy into? What are the Docker credentials I need to pull the images that I've set up for doing this serving? What do I want to create the ingestion database this time? So that's the, should I create it? And where is the database, where do I want to run that ingestion job? So what cluster, what do I want to ingest? I want to ingest these documentation from the sitemap. the Azure DB credentials. So the first thing that's done by this script is to place the model namespace that you've specified for all the parts that you want for this model serving across all of the clusters. So that's a policy, the spread policy, spread and duplicate that namespace across all my clusters, and spread and duplicate the image pool secret across all my clusters. So that's step one. Yeah.
Is Astra DB something like maintains a persistent store?
It does.
Okay, so on it's like backed by S3. When you spin up, it pulls into in memory and flushes to S3 periodically.
So that's true. So the thing that we did with open source is exactly that. We used Face, which is an in-memory database, and then we populated Face. We pickled and flushed it to S3, and then when we wanted to use it, we pulled it in from S3. But Azure DB is a live database that's persistent and has all these features built in. And this is a person who works at Azure DB. So any more questions about that, you can refer to him. But basically, we didn't have to do that extra work of pickling and writing to S3 because all of that is built into Azure DB.
Awesome. Thank you.
But you'll see both of those kinds of databases in the GitHub repo. So the next step I've done that is to set up my LLM serving. So this is my model that needs GPU resources. So I set up a policy that says, I want this model placed somewhere that has sufficient GPU resources for this to run. And I've said how much GPU resources I need. And then I deploy it and I deploy a service in front of it. And so that policy is resource availability. So it looks at all the clusters that have enough GPU resources that I'm specifying and chooses one of them. And so when that's done, I have an external IP, which I'm going to give to later to my front ends. So this was your question of how do I know who to talk to? Next, I'm going to place the DB ingester job on that one cluster that I'm only using for ingestion. So otherwise that cluster's in standby. I'm going to pull the data from the static place, and I'm going to run the job for ingestion. And yeah, so this is a specified cluster policy. And so finally, I'm going to write those three front ends. I'm going to use a policy of spread and duplicate, but I'm going to spread and duplicate to labeled clusters. Those special clusters I set up in the three regions of the world. I don't want to spread on all 6 of my clusters, just the 3 that I've labeled. So I'm going to have this spread and across subset policy. I'm going to deploy those front ends for RAG, and I'm going to have each of those. There's going to be service in front of each of those 3 regions. And these are the addresses of the services in front of each of those 3 regions. And now I'm going to make a query to version 1 of my model. So I'm going to choose one of those regions to make a query. Now I could have another load balancer in front of it to choose the region, but this is, that's an implementation detail. So I'm going to make that query and it's going to work. So now I'm happy. Now I look at Nova. Most of my clusters have been woken up. They're not in standby anymore, and they're in status. And only one of my GPU clusters woken up. That's the one that I chose to put the GPU workload. So now I'm going to roll out version 2. Version 2 rollout is very much like version 1. So we're going to kind of fast forward through this. The only thing is I'm not going to set up the vector database again. I've already set it up, but I actually want version 1 and version 2 to work on the same vector database so I can make sure I can compare apples and oranges as far as their performance. So that's kind of, I've done that on purpose kind of thing. So I'm going to deploy version 2 in a different namespace, and I'm going to make a query to version 2. So pretty much the same thing, except we skipped the resetup of the ingestion database. So now 5 of my 6 clusters are busy running workloads. And so that second GPU cluster got used by my second copy of the model. So now both my GPU clusters are busy. Now I'm happy with version 2. So I decide to retire version 1. My script retires, and my script just runs a deletion of the namespace I was using for version 1. So that namespace gets deleted from the control plane, and it gets deleted from all the workload clusters. Whenever I deployed that namespace to all the workload clusters. So now I'm back to one of my GPU clusters is idle, and so it's all good.
And there's a question.
Yeah.
So in a request reply service mode, you would usually monitor the CPU utilization, memory utilization to understand if within a cluster, do I need more instances of this
Yes.
container? in the GPU world, how do you measure those things and how do you scale within that cluster?
That is a very good question. That actually feeds into my example too. So we just talked about Nova, which is a control plane that's handling workload clusters and scheduling according to the resources that are there. And we've talked about those resources being static, right? I look, I see how many resources there are, and I make a decision. But what if there's a cluster autoscaler running in one of those or any of those target clusters? So Nova understands that. It understands that there may be the cluster autoscaler that you can get with Kubernetes, or there may be Elotl's autoscaler, which is called Luna. So Luna is a cluster autoscaler that runs on any particular cluster, and it can add more GPU nodes if, for example, the GPU nodes are needed. And it depends on, so it's two things. If you're actually allocating something, which in this example we'll do, and that pod is pending because it can't be placed, then Luna will directly add nodes. If you need more resources and it's an application level thing, then you would be running the horizontal pod autoscaler. And then Luna would see that there's pending pods resulting from that, and it will add nodes.
Okay.
So yeah, this is exactly, thank you. We're close to the end. I know we're running over time, but we have first two steps are the same. You just saw roll out version 1, roll out version 2, but now you're out of space because I have an artificially small GPU cluster. It has one A10 in each cluster, which is pretty expensive anyway for somebody who doesn't have much money. And so now I can't afford to roll out version 3 of the model. But one of my clusters is running an autoscaler. So Nova sees that. It realizes that, okay, there's not enough static resources both places, but I'm going to go ahead and put version 3 of the model on the cluster that's running the autoscaler. And so that's what it does. And you'll see that example in the GitHub. So that's exactly what we say. So anyway, done? We're done. So we want to argue that we've taken something like multiple clusters, which adds complexity, but it lets you manage resources in a way that you might want to do to group them according to their your needs around regions, around availability. But we've made it easy to do with policy-based placement. And so we think it's a kind of a good, easy button for doing resource handling efficiently. So that's it. I guess we've taken questions all along. So, but we do have a free version of Nova. So please feel to try it. There's other things Nova is good at, and you could also try Luna as well. So thanks a lot. Okay.
Hey everyone, thank you for sticking around. It's a very long day. And I think we'll continue the same conversation. And we'll get more specific about the workloads we will run in the clusters. But I heard a few things that I think you will hear me repeat in this talk. But to start off, I want to ask what you guys think about when we talk about batch workloads. Any adjectives that jump in mind? Any descriptions?
Game scheduling, right?
Game scheduling, okay.
Yeah. Good one.
Yeah, it's a good one. Anything else?
AI.
How to operate across different executors?
How to
distribute the work across different and collect the result of the work back.
so sort of a map reduce kind of thing.
There are two scientists, one of Jeff Dean and are those Jeff Dean and Sanjay Gamawat?
No.
Oh,
No,
okay.
that's scientific. No, I will look this up. Yeah, so they are really big processing jobs that run on and try to process large amounts of data. They do map reduce. They're pretty much used everywhere. Like you may be using or running batch workloads without really thinking of them as batch workloads. And give some examples here, but like even the RAG, the ingestion pipeline, that is really a batch workload. You're running ad hoc experiments, deploying ML models and doing like A/B testing between models. That's a batch workload. Processing, geospatial data, processing mapping, originating maps, and all kinds of things are batch workloads. I think most of the AI world is really still running as batch workloads. There is like a tiny percentage where you're like this final bit when I'm serving the response from a model where you want the real-time responsiveness from the service is when you can think about deploying services or running them as services. But then everything else, I argue, is really a batch. And thinking about batch workloads in a different, running them in a different way than running services can have its own challenges and also give you a lot of benefits because it removes some of the assumptions and requirements that, this thing has to be, alive all the time. I have to call it at any time from any server, from any source, and it should be able to scale up and down. It should be very elastic. It can, automatically adapt to my request sizes. I have no idea about the client. How are they calling me? These are all the problems you have to deal with if you're running the service, right? You don't know who will be calling you when. But when you start thinking about batch workloads, you have a lot more control because you are running, you're like consciously deploying something, you're consciously running an ingestion pipeline, you know the data that's coming in. There's a lot more that you know, and you can use that to your advantage to optimize how you allocate these jobs. You can optimize where they run, and you can build back better. You can do a lot of, tricks to get your job done more deterministically. And I just want to walk through hypothetical example. So assuming, let's say there's one scientist that is trying to run a big data prep job, right? So they start running things on their laptop. They know Python. They write some scripts. And then they very quickly realize this is not going to fit. I need to process a lot of data. What do they do? What they can do today is they learn Docker to package all the examples and share it with us. And then after they learn that and build it, and probably incorrectly, but they will build it anyway. Then they have to learn some YAML to then write a deployment or a Kubernetes job spec or something to then go learn how do I do this on Kubernetes and how do I scale Kubernetes, like all of these constructs, so they can just get their thing that was working on their laptop, just running on a bigger machine, essentially, or distributed architecture, and then they're happy. And this sort of works, right? You can live with that. That is a pretty significant delay. You can live with this if it's just one person doing this job on one cluster, maybe. They will deploy it once. They will not have to maintain it or scale it up and down a lot. That's okay. But it gets crazy as they try to. I can promise you, it's not this dimmed on my laptop. Here we go. The ecosystem that they eventually find themselves have to deal with is just crazy, and it's like this is probably an exaggeration, but it is crazy to try to figure out all the tools you need to scale your clusters and the frameworks and this and that. How do I move data? How do I track the data? How do I sandbox the data? It's just super hard, and it gets even harder when you throw in one more person who's trying to share the same cluster. So you want to run one fine-tuning job, and then another person wants to run this. I want these many CPUs and pods, and then the other person wants the same thing, right? And then you run into crazy challenges. Well, one, I tried to categorize them in a few buckets. One of them is resources. Well, how do I even know that there are enough resources? And we, the previous two presentations talked about few tricks, a few ways you can make available these resources. But resource contention is a real thing. How do I do a distributed training job without starving? If two people are running at the same time and they just saturate the cluster with half of the jobs they need, you're done. Both of them will be waiting forever. how do I even know that clusters have capacity to run my jobs? And of course, probably everybody who's running Kubernetes runs against very low utilization because of the fragmentation. These batch jobs, some of them can run for hours or days. Some of them will run for a few seconds, and you end up with very fragmented machines that are sticking around, and you can't really fit your new jobs. And bin packing is not great, and all of that. Multi-tenancy, where your typical enterprises, you don't create a cluster for every person, right? You have clusters that are shared across, and multi-tenancy becomes a real problem. How do you allocate resources for maybe individual teams? How do they share these resources? And there's some native support to some of these in Kubernetes. So you can start creating resource quotas, you can do node groups, node pools, you can do some to get a sense of partitioning in clusters. But it's not great, not to get you all the way. And then this whole class of problems around data. How do I even get the data set that I want to train, let's say, on available for my job when it wasn't even produced yet? So maybe I run a job that does some data transformation, then I want another job that will do the training. How do I sequence these two jobs? There are no native constructs like this in Kubernetes that can sequence jobs for you. How do I know that the data that I'm accessing is the same data I just ran with? Because somebody else may have run and changed the S3 bucket or changed the data there or removed the column or did anything. There's no visibility into this. You're just running jobs, and the cluster, nothing in the cluster protects against or understands is data aware, doesn't understand what you're trying to access. And then, of course, there are operational challenges. And besides just maintaining Kubernetes is a challenge, when you throw in tens of thousands or millions of jobs at it, you will not be able to schedule it. You'll not even be able to create the pods. And I'm sure you're familiar with these problems. We have customers who run tens of millions of pods a day, and we on a vanilla cluster, somebody will have to be sitting around retrying jobs and figuring out, looking at which ones ran, which ones failed to even get scheduled, and retrying all of this till they get a success, which is is not a sustainable solution. I would argue. You may think otherwise. And there are quite a few solutions in the, I'm looking at the open source landscape. I don't know if Luna or Nova are here, but I assume they should be. But there are a lot of solutions that in the open source community that are trying to solve some of these problems. And there's gang scheduling, as Brian was saying. They do out of cluster scheduling, so you can avoid the API server rate limits and HCD scale limits. You can switch to multi-cluster if you use Armada or Armada, but then you're still left with a lot, I guess, to look for. You still have to maintain your own Docker images and dependencies, and you have to tie these with your code. You have to understand the dependencies and be able to schedule things the right way. There's no data awareness, and the rate speed is just trash, right? Like if you're comparing this to running something on your laptop, this can take hours to iterate on something, or at least minutes. Whereas running on a laptop is just you change one line of code and you run again, right? And none of these solutions, I would argue, gets you to this nice experience of developing on your laptop. And then observability, obviously, is just an exercise left to the reader, right? You have to set up your own metrics and maybe Prometheus and wire it to Grafana and do your own thing, or wait some biases if you're training. It's just all on you. And I guess after looking at the existing solutions and the problem we're trying to solve, and reminded of this infamous quote except that I found it's not really anybody never said that. But the code is I think is still valid. That the existing solutions look to me like they are trying to take the same paradigm, the same pattern, the same way Kubernetes offers to run jobs and make it better. Right? It's not fundamentally different. They don't try to address the real problem of somebody, a data scientist, trying to run a batch workload. They're too low level, and they will remain this way. And I think for a good reason. Like you want the fundamentals to get better. You want the scheduling to get better. You want these native constructs to get better. Just not enough to solve the end user problem. And as with a lot of computer science problems, the solution becomes just add one more layer of abstraction. And this is where we introduced our open source project. It's also a Linux Foundation project called Flight. We started the project in 2016, 2017, open source 2019. It has been in the market for a few years and used by a lot of companies. I'm showing a few logos. We'll can show them in a bit later. And here are some of the summary of what it gives that isn't found or maybe more complementary to the current open source landscape. It has a higher level DSL, right? So you don't describe your jobs in YAML and you tie them with Docker files. There is a DSL that describes the parts you want to run, describes your images, it describes how you tie the jobs together and how you pass data around. And it is K8s native, so you can continue to leverage all the existing, the better schedulers. It's not trying to replace any of these tools, tries to work with them. It has its own out-of-cluster scheduling, so it averts the all the bursty load problems and gives you multi-cluster, multi-cloud out of the box with very similar architecture that will again the control plane and agents, and they have a diagram to show that. Is strongly typed, so you are aware of or the system is aware of what sort of data types you're trying to pass between jobs. So it's not just a pod with a command that you want to run on a Docker image. It knows the interface, knows the input, what should the input look like, and what the output it expects you to produce look like. So you can, before even running anything, it run a compiler and can detect if the thing will run or not, even if it's a distributed job that will run on tens of thousands of pods. It's data aware, it's version immutable. Talk about these in a bit. Here's a high-level architecture of the system. On the left, you have your same scientist that was accessing the system through UI, CLI, code, and so on. There's a data plane of few services here, and a control plane and a data plane on the bottom with just an operator that operates on a custom resource, we're calling it workflow, that defines steps that needs to run and how you pass data between them. And the job of that operator is to create pods when needed. Create one or more, depending on the job that it needs to run right now. So when it knows, it's monitoring all the pods that need to run and the ones that are running. So when they produce the data, it then can run the next set of pods or the pods that they depend on. So it has the dependency graph and it knows how to move things around and updates the status back to this CRD. The control plane maintains state outside of the cluster. It's not using CD with a Postgres database and a bucket and so on. The data is all durable. And the goal is that you can rerun the entire workflow and it should produce exactly the same data, assuming your code is deterministic, obviously. But it makes sure the data that's given as an input is sandbox, and when you're writing outputs, you're writing in a sandbox in the bucket in some cloud buckets. So no two jobs can like interfere with one another. It can do caching on the nodes. So it can, since it knows the dependency between tasks, can make sure the following task run the same node of the producing task. So it avoids the re-downloading of inputs and so on. So you can do a lot of smart things about scheduling because it understands the graph, it understands what you're trying to run, not just the one-time optimization of a big job. Any questions so far?
And this question.
Oh, yes, please.
So far so good. What I'm trying to understand is, so someone who is in Kubernetes ecosystem, this podding orchestration and managing the pods, splitting the graph, workload into graph, this all makes sense. But let's say someone is coming from a Spark execution environment.
Yep.
So it looks like to me that it has already been solved in that ecosystem. And we have things like AWS Glue, which offer serverless based orchestration of it. So I don't even have to worry about where is my admin console, where are my Kubernetes pods. It's all like abstracted away from me.
Yeah.
I just run a Glue notebook, and when I'm satisfied with the output, I schedule a production thing for it within the same console itself. So does it make a lot of complication go away if I'm not in Kubernetes ecosystem for a batch workload?
Great question. And I have two things I think to add here. A lot of our customers run Spark here. So the propeller, instead of creating pods, it can also create other CRDs. It can create a Spark application CRD that gets scheduled, like an ephemeral cluster. And a lot of customers do that because they want ephemeral clusters to make sure there are they're clean clusters, right? No two jobs will affect the dependencies or run into, for I guess others, if you haven't used Spark in some of these persistent environments, they stand up a cluster, or you configure a cluster in a Spark cluster, right? The MapReduce cluster, and then people can submit jobs to this thing, and this job pretty much looks like a graph of dependencies, things to run on this one cluster. There are many problems with that paradigm of running things. One of them is dependencies, managing dependencies, because the person who created the cluster is the person who controls the versions and the dependencies and what can and cannot run and so on, not the individual who's trying to submit a job. You just have to use what they specify, right? And then these clusters can also get not corrupted, the data corrupted. So people can do things to the cluster that are irreversible. And when somebody runs a job, somebody else runs a job, they will have to deal with the unclean cluster that you are left with. So the direction I see a lot of people are moving to, even like Databricks started supporting this, they're calling it ephemeral clusters. So you create a cluster, you run your job, then you delete the cluster. The next person runs, does the same thing, create a cluster, right? So for that, people do like to run this on Kubernetes for the same purpose, right? You're reusing the nodes, so nodes are around, especially when they're like busy and multiple people are submitting jobs. You don't pay the penalty of allocating nodes and bringing them up and so on. And these are just containers. If you run the cluster in multiple containers, Kubernetes set up the network for you, and you starts up, you submit the job, and dies, and so on. So that's one. And two, there is a benefit in splitting your job into multiple distinct execution units, not a single Spark job. There are a few benefits there. One is reproducibility. So you can cache and reproduce the parts that haven't failed. Like somebody was talking about the GitHub rerun failed work jobs example. With Spark, you will have to run the entire job. If one part fails, the last part fails, you still have to rerun the full job again. If you split your job into multiple parts, the parts that succeeded just get cached and never have to rerun again. And the part that you're iterating on is the part you keep rerunning until it succeeds.
So it's like several distinct step functions put together on top of an orchestrator, where each step function has a distinguishing on success, do this, on pass, on fail, do this. So if you fail, only the last step function has to be read.
Yep. But yes, great question. I think the same, I don't know if you're familiar with Ray, it has similar setup where, you run multiple, you can run a graph essentially, but the same thing, you have the failure unit domain is the entire Ray job. So we see people very often split those, even into multiple Ray jobs running in flight, just so they get the caching and they don't have to rerun the entire job when something fails, semantics. Also, of course, you get observability, so you know where are you in the stack, in the graph, how far along are you, and so on.
So is Flight one follow-up?
One more, yes.
Is Flight like an ecosystem that provides wrappers on top of common map reduce operations, or is it a orchestration tool, just an orchestration tool? So if you draw parallels with Spark ecosystem, Spark gives you adapters for interacting with like the S3 buckets, SNS, not SNS, the other modes like databases, JDBC connectors.
Yeah.
So does Flight provide equivalent adapters for interacting with most commonly used things?
Yep.
Not just an orchestrator per se.
Correct. So I drew the simplest example because of orchestrating pods, because we're talking about Kubernetes. But this may not be pods. You might be orchestrating service calls, or other kind of things that do compute. Containers is just the simplest basic example. But yes, it has abstractions for a lot of these things, and you can build your own extensions too.
Thanks.
I was just going to ask about the use case or the control plane for the message queues there, but I assume it's just like status passing and stuff like that.
So it's there are outgoing and incoming events that it supports. So you may say when let's say data is ready in this location, kick off this workflow.
Oh, okay.
And that happens through, SQS,
yeah,
sending or receiving messages. You send notifications if you can configure to send notifications when workflow fails. So people commonly send Slack notifications, things like that when their workflows fail or page are due. All right, and this is an example of the code you would write. There are 3 parts here. So there's this abstraction called image spec, which is a wrapper on Docker files. You don't have to use it, but we built it to abstract away the common patterns we see people write Docker files, so we can write the Docker files for them efficiently. We can layer things correctly and make sure they're cached most of the time when they get built and so on. And then there is your execution unit. And again, I'm using this example, the simplest example. This will turn into a pod, but this doesn't have to be a Python function. It can be a service call. It can be a lot of other things. But the simplest one is you write a Python function and decorate it with add task. That automatically means this will run as a pod. You can give it an image or a Docker file, or Docker image that you built yourself. You can give it resources. You can say, I need 2 GB of RAM and I need 2 GPUs and so on. They will turn into just pod resources. You can say it's cached. And because we know the types of the inputs outputs, the system can automatically generate, consistent cache keys, and it can know, should I run this, or I already have run this before, and I will just use the same output again. And it's one of the benefits of strong typing in the system. And then lastly, you create this workflow, and this is where you define your data flow. This is where you tie multiple tasks or other workflows together with the inputs outputs, right? Which is just a Python function again, right? It takes an input,
and you're calling one task, take the output of that, call another task. If you notice here, I also run a map task. So you're saying, instead of running say hello once, I want to run it for every user from this list. So it will automatically generate n number of pods to run these jobs on the cluster.
Can I ask you some more about the optimization that you're doing in the image spec building piece? I imagine with something like this, it would be pretty advantageous to try to make the container as small as possible, especially if you're gonna have to spread it out to a bunch of different nodes, thousands of nodes or whatever. So is there some intelligence built into it to do like staged builds if it can, so that when you finally get to the actual container that you're running, you don't have any debug libraries or other build artifacts. It's just the binary.
It's just what you're running.
Okay. Nice.
I
mean, that would be great to have just on its own, honestly, because there's everywhere I look around.
Very bad look at
Massive containers that you got to ship around everywhere, and they take a long time to move.
Also, if you're using the same, they are composable. So if you're using the same image file, image spec, but you want to add one package for one task, it's aware of this. So most of the layers will be the same, and only one package will be added. So it will speed up, of course, like passing images, not passing, the downloading images, I guess, on nodes. And as you can see, you can have different tasks point to different images, and they are all used in the same workflow. So they find with the abstraction, the container here is the sort of the pod spec, which has its own image. And the data passing is consistent, right? It's just passing S3 links around that are built in the system at runtime, like sandbox, where and what to add. It is used in a bunch of companies. There are a few thousand more than what I could fit in, in the slide. But these are some of the notable maybe logos that might look nice. Some of them, maybe the one in the bottom corner. And then this is the company I work at, Union. I'm one of the co-founders in the company, and we started with the open source project. So we built the open source project back at Lyft, then open sourced that, and then started the company to build a business on top of it. But we are trying to take a slightly different approach. If you're following all the open core company use, between HashiCorp, Grafana, Elasticsearch, there is a lot of struggle, I would say, the least, because I think the fundamental problem is the theory was you build all the IP in the open source project, and then you go figure out monetization at some point later. And it's not quite working, I would say, for most people. So we are trying to, from like the get-go, we wanted to build distinct value, distinct IP in the company that is not the open source project. So we're leveraging, the best we can do in open source. We're still investing there. There are a lot of amazing contributors already on the platform, but we want, our own IP that is very distinct in the company, and we want people to come buy our product because of that, not because we are the guys behind Flight or because we host Flight. That becomes sort of a side job, not the core of the business. So we did build a few over the past 6 months or so. We built artifacts since first class support for like model registry and data sets. So the system now understands them. It can track usage of data sets even across very distinct workflows that are not talking to each other. It knows that you are using the same data set here and there, or maybe this workflow produces a data set that some other workflow is using. And you can see that, visualize that in the UI. You can put some policies around, the schema changes and evolution, and making sure you don't break somebody else accidentally. who now understands the data and the model schemas at the system level. We implemented a sort of reuse pods, which breaks the paradigm of Kubernetes, I guess, but it showed us a lot of great potential. The best we could get in, like, if you have even the node up and you're trying to schedule a pod with large containers, especially, it takes seconds, right? Like we can't get around that. Every pod that runs on the node will take seconds just to boot up. And that was just at some point not acceptable because people are trying to lower the overhead of the system as much as they can because they want to push like the batch workloads all the way to maybe real time. It's not going to get there, but they're trying to push this way a lot. And we figured that if we know, because the system knows that, again, it knows the graph, it knows exactly the tasks you want to run in what order, what data are you passing, which images each task is using. So it can make a very informed decision that I will keep this pod around and I will submit another job to it. We'll wait for it to finish and the data is already written to disk. It's no download of new data around, and there's no downloading of image. The container has already started, so the runtime is in memory, and we are seeing like 80 or even more % speed up, where like can run entire workflow that used to run in a few minutes in seconds, just because you're not putting up more pods all the time. And then, of course, we added observability out of the box. So you run the same workflow and you know exactly in real time, you see the CPU memory in context for this one task. You get the real live logs. It's just piping through Kubernetes logs. But you don't have to know about Kubernetes even if we're running on Kubernetes or not. You're seeing metrics and logs in real time. VS Code wired up and a bunch of other things, but yeah. Skip this, but you were asking about other integrations, and there are like a bunch of other things that come with the platform that are not just running pods. But you know, we'll skip through this because I think I'm already over time. This is sort of the architecture we have at Union, and that's what allows us to run multi-cluster, multi-cloud support. Very similar, very typical. Each cluster that runs on a customer in a customer cloud. It has our own operator that connects back into our control plane, and it does, you know, schedules the pods and whatnot on the cluster, and you have access to all of your data and resources that we have no access to. It's always calling back. There's no, you know, ingress into the cluster. And then on our side, we have, you know, our own services and storing metadata about the jobs and so on. And then users continue to use a familiar interface. So all of their flight workflows run just right out of the box, but now they have access to all of this. Yes.
So the question I have is, this is one mode where you ask the customer, bring your own account. Are you also like Databricks who say, I provide you API, I abstract the compute and all those details?
We just launched the serverless offering where, again, same consistent interface, and we are just doing this in the back for people. Yes, but it's for enterprises. We're not Databricks, right? We're not the size of Databricks where people would trust us to run their thing or have access to their data, or actually give us their data. So we see like this will stick around for a while, where enterprises would want us to continue to deploy within their accounts, just so they can have their own policies around data access and retention and so on, that we don't. But yeah, smaller, like indie developers kind of thing, love the serverless. You just pay as you go, and yeah. And yeah, with this, thank you. Appreciate it.